So after having this k-means clustering algorithm done, we have identified which are the probable classes. We are now going to assign a class to each of the observation. So this new class category shaded in blue is going to be our response variable for all the predictive classifiers or the predictive models that we are going to build to classify any out of the sample still grid to be belonging to class 2 or not class 2. That is the sole objective. Okay. So uh, this this is I guess you are pretty familiar with what I mean to say by response variable. That is, response variable is the output. To every input, there is an output. That output is the response. Okay. So you see this number 2, 2, 1, etc. They're all. So we have found 3 classes or 3 clusters. So I'm calling now on each cluster as my class. So I'm just putting this number. So every entry must have a class. So I'm putting that class here. So that is how I obtain this class category column. Okay. So these numbers 2, 1, 3, they refer to the levels. So these levels are quite clear. And we also wanted to convert all the predictive variables which are categorical type. Categorical refers to those variables which do not have any numerical significance. Say yes, no, or male, female, true, false. These are all called as categorical variables. Okay. And we wanted to make sure that all our categorical variables are converted into factors. So factors look like numeric, but they do not have any numerical significance. They are called nominal variables. And the only categorical variable that we had here is the processing condition, which is denoted as X. So let me go back to the previous slide. We had 9 different processing conditions, okay, of the semi-finished steels, indexed from 1 to 9. And these are abbreviated as A, C, D, N, and so on. So A refers to annealing, N for normalizing, CD for cold rotating, and so on. So all these 9 categorical levels are all included here. So the programming language or the platform that you are using, say Python or R. So I'm more conversant using R. Python I do, but I like working on R. So you don't have to do, say, with some thousands data manually. You can't change it. So these are taken by those platforms. They do these things for you. So these entries that you see against this processing condition, when not done by me manually, the R program itself can generate those numerical indices. Is that clear? Just again, I'm going to quickly ask you, until now, is everything clear? Okay. Okay, thank you. So we also wanted to just let me tell you that in any supervised machine learning algorithm, we kind of split the data into 2. One for training the model and the other for testing the model. Okay. And when you split the data, you must remember 2 things. One is that the data, any data has some degree of heterogeneity or randomness, and that is what we expect that to be present in our data. As random it can be. Okay. That randomness should be equally spread between your test data and training data. Suppose, to give you an example, I have a single column where you have, there could be other observations too for each entry in that column, but I'm assuming there's a single column where I have entries of some 140 boys and say 60 girls. Okay. Now I'm asked to split the data, but I have split the data in such a way that one data set has more boys and the other has more of girls. That's called a biased data set. So because when you're going to train the model will be trained on the training data set, which is highly biased, which has more number of boys. So there's no point. So I have to have a kind of mix-up data containing equal number of boys and girls in the training data, or the ratio of the boys and girls in the training data should be equal to the testing data set. So that's called the heterogeneity in the data. That is something that one must take care of. So we had done that job. We have made sure that the heterogeneity or randomness in the data is kind of distributed equally between the training and the testing data set. Okay. And it is sometimes required that we go for feature scaling or feature normalization, especially when your work is to do only prediction. But in our case, we also wanted to do some intermediate analysis of the coefficient. So we did not actually go for doing a feature scaling. That was not our job. And we also found that our data set that we had, the original data set, was not balanced well. So it had more number of zeros than the ones. As I told you, having such a biased data would cause the model to be trained in such a way that it will be correctly predicting the zeros. So I'll tell you what are the zeros and what are the ones. So it can correctly predict anything out of the data, even if it actually comes to the category 1, it will predict a 0 because it is trained. So I'll give you an example. Suppose in an examination, you start preparing for examination. I've given you a set of books, and you have during your preparation, you have learned everything from the book. You have kind of learned by by cramming the things. Okay. Now, what if I ask you question paper? I mean, I set a question paper, and the questions are all included what you have studied from the book. Are you not going to score 100 out of 100? I mean, uh, I'm hoping that you are getting my point. So you're kind of trained uh, on the data that you are kind of provided with. So if I ask you any question that is outside your curriculum or syllabus, you'll possibly fail to attempt. So that's exactly what we are doing here. If I am training a model with a very skewed data or biased data, as I told you, if I have more number of zeros in the model, in the training data set, your model will be trained to only predict zeros. Even there is a 1, it cannot predict that to be a 0. So we must take care that the data set that we have has a balanced distribution. There must be equal number of zeros as well as equal number of zeros and ones. Is that clear? So there are various techniques available, but the one that we used is what we call as the traditional S-mode method, where we resample the data and generate new data for the ones. But if you want to specifically understand how this is done, you can write to me. I'll possibly discuss that in some other note. Okay, so this is how we kind of made a balance between the zeros and the ones. Now we are ready to build up the predictive model. So we are going to build several predictive models such as logistic regression, then what I call that as regularized lasso regression. Then we have decision tree and something, the most popular model, which is random forest. So I'm going to show you, get you familiar with all the models. It might get, so don't just go by the time that I mentioned, 8 to 9 p.m. It might go a little beyond that, but I'll try to stick to that. So all these models will give me some kind of accuracy, and I'll choose the one that has the best accuracy. So the idea is how to select the model from the accuracy and the performance. Okay, so we came up with the idea of building a logistic regression model, and this technique works best when you have the response variable, which is dichotomous or binary in nature, yes or no, 0 or 1, true or false. But if you have a third level in the response variable, then going with logistic regression is not a good idea. You have to keep, there are ways to do that, but preferably we go for, so as in here, there are two things that I'm categorizing my data into. Whether, I mean, one is anything that is belonging to class 2 and anything that is not belonging to class 2. In that not belonging to class 2, you have class 1 and class 3 included. So I'm calling, if it is anything that is belonging to class 2 as 1 and not belonging to class 2 as 0. Is that okay? So where was I? Okay. So as I told you, so this works best for response variable, which is dichotomous or binary in nature. Now, it happens that in presence of more than one single predictive variable, okay, if you have 2 or 3 or 5 or many different variables, it is really difficult to visualize how this model works. And to make it simple, I thought I'll possibly model it with one single predictive variable, which is percentage carbon in this case, and try to extend that model with multiple predictors at a later stage. So having this response variable plotted against percentage carbon, how are we meant to draw a line of best fit? We could do this and we get some kind of regression output which looks like this. And it appears that as my carbon percentage increases, the chance that a particular grade of steel belongs to 1, which is class 2, keeps decreasing. Okay, so the response variable here refers to or represents the states of the training data, which could be either 0 or 1. So since I'm bringing the word chance here, I'm kind of implying that it is actually the probability that any out of the sample steel grade will belong to class 2. Okay, class 2 or not class 2. So this line in theory is actually modeling the probability. But this line has a theoretical problem because at higher carbon percentage, okay, so I'm now referring my response variable or the y-axis as probability. So at higher carbon percentage, you can see that this line extends to the negative domain, the negative regime. which for probability sets just don't make sense because you cannot have a negative probability for. Okay, so using the least square regression method doesn't help. So what we thought of is replacing this probability with a term called as odds. So the odd has a formula like it has P on the top, and that is the probability of finding a particular grade of steel to be belonging to class 2. And in the denominator, you have 1 minus P. Sorry, I have not shown that equation here. So it is P by 1 minus P. So what is 1 minus P? 1 minus P is the probability of not finding that steel grade in class 2. So the numerator refers to the probability that the steel grade belongs to class 2, and the denominator says what is the probability that the same grade of steel doesn't belong to class 2. Okay, so that is going to be my odds. So at odds, if your probability is say 50%, then your odds is equal to 1, because P by 1 minus P, that is 0.5 divided by 1 minus 0.5, which is 0.5, gives you odd of 1. And if your probability is as high as 1, then your odds can go to infinity. And you can see between 0 and infinity, the middle value is 1. And also, like between 0 and 1, these odd values are kind of compressed and compact. While beyond 1, these odd values are distributed sparsely. So if you were to draw an odds distribution, this would increase a lot fast and then decrease. This would show a right long tail. Now, this line, what I have represented here, is still better than what you had seen in the previous case where we used probability as our response variable. But this again suffers from two problems. One is that, as I told you before, at higher carbon percentage, this line also extends to the negative territory. And you have seen the lower value of the odds is equal to 0. Okay, and furthermore, let me tell you, any machine learning or supervised machine learning algorithm, you have this response variable as close to a normal distribution. But in our case, we see that this distribution is quite skewed. It shows a right long tail. So using odds also does not help to solve a problem. So what we decided then to use something called as a log of odds. Now, this is really super convenient because the range now goes from minus infinity to plus infinity with midpoint as 0. And you can also see that this middle value is 0 because log, so at 50% probability, your odds is equal to 1, and log of 1 is equal to 0. So my response variable is kind of nicely distributed and centered around 0. So you are approaching towards a normal distribution. Therefore, we decide, and most importantly is that we have created something that was earlier having a range from 0 to 1, and now it has a range from minus infinity to plus infinity. So at any percentage carbon, your response variable, which is log of odds here, is not going to create a value outside its limit. So it's all contained in that bigger limit of minus infinity to plus infinity. Let me see, somebody has put up a message. I'm not sure if somebody was logged out. Okay. So we are going to therefore use this log P by 1 minus P. The single predictor equation is going to be our logistic regression model. So this is, as of now, it is showing with a single predictor, which is percentage carbon, and my response variable, which is log of P by 1 minus P. This is a very good model. So we can reduce this further to a very complex exponential function or exponential equation. And you can see that this equation is nothing but a function of probability. So we are once again back into this probability versus percentage carbon plot. And this function takes the shape of something called as a sigmoid curve. This is for people, those who have studied metallurgy. You have learned about sigmoid curve when you read about TTT curve, the way these are generated. So sigmoid curve is this typical shape of the S curve. Okay, now given any percentage of carbon, you can determine the probability that it belongs to 1 or class 2. Okay, so 1 here refers to anything that belongs to class 2, and 0 is a non-class 2. So this single predictor equation, which is shown with percentage carbon, can now be expanded using multiple predictor, showing all the predictors and the coefficients clearly specified. So these predictors can be either categorical type or numerical type. Again, in numerical, you have continuous numeric and discrete numeric. And what does this coefficient show? So the coefficient tells us what is the, how strong are these predictors acting on the response variable. So remember, coefficients are not always slopes. Slopes are coefficient when you have a linear model. But if you have a polynomial model, then slopes and coefficients are not the same. Okay, keep this in mind. So all that the coefficients tell us is how strong this each predictor are acting on the response variable. Okay. So we have come up to this, and now I'll tell you that we have obtained this histogram of the predicted success probabilities, which shows a nice dichotomy in nature. And looking at this, we decided to put a probability cutoff. I'll tell you what this probability cutoff is. So having this a very symmetric distribution, we thought of having the probability cutoff somewhere between 0.4 and 0.6, somewhere in the middle value. I chose, so 60% of my data, as you could see in the histogram plot, has probability value higher than 0.5 and 40% lower than 0.5. Therefore, we decided to have the probability cutoff somewhere between 0.4 and 0.6, which is 0.5. So what is this probability cutoff? So probability cutoff is a number which will tell me if I'm predicting something, some out of the sample or unseen sample or unseen observation, if that value is higher than the cutoff value, I can consider that particular skewed rate to be belonging to class 2 or 1, and anything that has a value of probability, because what we are finally aiming to do is to calculate probability of any unseen observation. So if that calculated probability value comes below 0.5, I'm going to consider it to be in the non-class 2 category. So that's where I put this probability cutoff. But what if I had a distribution which had the peak around the lower probability values? So in that case, I have to, to make it more simple to understand, say, suppose your calculated probability value is 0.3. Now, can I tell that, well, 0.3 is a very low value number, so that doesn't mean that it belongs to class 2. It obviously belongs to the non-class 2, but that is wrong. So just don't go by the numbers. Numbers, many times, that is where data scientists make mistakes. They don't understand oftentimes how this distribution, because most people I see are blindly working. And let me tell you, let me make this point very clear. Data science, AI, ML is not everyone's cup of tea. Take it from me. In India, I mean, I see many students are from Bangladesh, Pakistan, India, and other countries. In India, it's a hype and a craze that everyone is running after data science and AI, ML. But if you're not good in mathematics, good in statistics, and you don't, just programming in Python or R doesn't make you a data scientist. Let me make you clear. So you can be a good data analyst, but not a data scientist. To be a data scientist, you have to eventually be you have to be good in mathematics and statistics. So distribution is very important. It should be visually clear to you what a distribution says. So blindly working on these models makes no sense. So there are people, and that's a sad part, because in India, I have come across data scientists who has no clue about normal distribution, simple normal distribution. So anyway, so if you have a distribution like this, is just let me understand, am I talking sense? Like, are all of you understanding what I'm saying here? Okay, thank you. Thank you. Okay. So what we are going to do in such situation where you have a peak towards the higher probability values, so it means that your data set, the training data set, has not been balanced well. So there were more zeros than the ones. So your model has started predicting the zeros correctly, but not the one. And that is why you are getting probability value towards the lower side. Is that clear? So in that case, what we do is push off this red line, that is, you see the midline, towards the lower side, somewhere around the peak. We call that as the probability cutoff. But that is not our case. Our case was very simple. We had a nice symmetric dichotomous distribution. So let us forget about this, but just this is for your understanding. I have included this. So, okay, now, after we have built up this model, it is important to understand how this model works. Is this a good model or a bad model? Can it be implemented or not implemented? And this is exactly where the concept of AUC, ROC comes in. So AUC, or area under the curve, tells me about the model's predictive ability to classify the classes correctly. Okay, so the term sensitivity tells us what portion of the positive classes are correctly classified, and the term specificity tells us what portion of the negative classes are correctly classified. So if your, suppose, training data set had the zeros and ones clearly separated out, nicely separated out, your model will be trained very well. So you have 50% data in no, another 50% yes. No confusion, everything is well separated. There's a clear demarcation between yes and no. So in such case, when you start increasing the probability cutoff, your number of true negatives starts increasing. Therefore, the specificity starts increasing, but that is not going to hamper or affect your number of true positives or the sensitivity. Okay. However, beyond a certain limit, when you further try to increase this probability cutoff, now your number of true negatives starts dropping down. So your sensitivity as a whole starts dropping down, but that is not going to affect the true negatives of the specificity. So usually at specificity and in such nicely distributed or separated data, at sensitivity and specificity equal to 1, your model will be able to predict the two classes correctly. But that's not what happens when we deal with real-time data or in real-life data, not real-time. So in our real-life data, most of the data are kind of mixed up. There are some overlapping classes. Okay, so it's not so simple to look at. So in such case, a small change in the specificity can cause a change in the sensitivity. So usually we try to find out that point about which the sensitivity drop is maximum. And we calculate the probability value at that point and treat that probability as my cutoff. So what we saw is in our AUC curve, we got an AUC value close to 0.89, which is not that bad. And we found that point where that drop in sensitivity is seen to be maximum. And we calculated the probability at that point, and that gave me a value of 0.6. Now, using 0.6 as a probability cutoff, we found that out of 54 test observations, 47 were correctly predicted by the model. So correctly predicted are the ones which were actually zeros and were also predicted as zeros, and which were ones were also predicted as ones. So that way we got an accuracy close to 87%. So that is the beauty of the logistic regression model.